Hello everyone, in this video, I will demonstrate how our 4-bit ALU design works and explain it. First, we have two multiplexers with multiplexer A and multiplexer B. First, let's look at the 4-to-1 multiplexer. A 4-to-1 multiplexer has 4 input and 1 output, controlled by two select lines X1 and S0. To build 1-bit 4-to-1 multiplexer, we use 2 NOT gate, 4 AND gate, and 1 OR gate. Based on the truth table, only one input is selected depending on S1 and S0. For example, when S1 equals to 1 and S0 equals 0, the output will be 2 because all other inputs are marked to 0. By placing 4 1-bit multiplexer together, we option a 4-bit 4-to-1 multiplexer. We use this structure to select 4-bit input A and 4-bit input B.
Next is the ALU, which is a 4-bit ALU capable of performing 4 operations,
which addition, subtraction, XOR, and XNOR. Let's start with addition and subtraction. These operations are built using 4 full adder. A 4 full adder consists of 2 XOR gate, 2 AND gate, and 1 OR gate. For example, when AI equals to 1 and BI equals to 1, CI equals to 0, the sum output is 0 and the carry output is 1.
When C equals to 0, the circuit performs addition. When C equals to 1, the circuit performs subtraction. The final carry output C4 is INOR. Now for XOR and XNOR. These circuits use 6 XOR gates. When the control signal S0 equals to 0, the output performs XOR. When S0 equals to 1, the output becomes XNOR. For example, if A0 equals to 1 and B0 equals to 1. When the S0 is 0, the output of the XOR operation is 0. Well, when the S0 is 1, the output of the XNOR operation is 1. The ALU operation is controlled by two select lines, which is ALU 0 and ALU 1. For the ALU operation, when ALU selector is equals to 0, 0 is addition, 0, 1 is subtraction, 1, 0 is XOR, and 1, 1 is XNOR. Next, the output passed through the feed floats.
On the rising edge of clock, the output captures the input value. When reset equals 0, the output is clear to 0, 0, 0, 0. The output updates again only after reset returns to 1 and a new clock edge occurs.
Finally, we look at the waveform to understand how the ALU produces its output. When the reset signal is set to 1 and a rising edge of the clock occurs, the selector for input A is set to 0, 0. So the value A0, which is 1, 0, 1, 1, is selected. At the same time, the selector for input B is also set to 0, 0. So the value B0, which is 0, 1, 1, 0, is selected. The ALU operation selector is set to 0, 0, which means the ALU performs an addition operation. As a result, the output of the ALU is the sum of A0 and B0, which is 0, 0, 0, 1. On the third rising edge of the clock, the selector for input A changed to 0, 1, causing the value 1, 1, 1, 0 to be selected, while the selector for input B also changed to 0, 1, selecting the value 1, 0, 0, 1. The ALU operation selector is now set to 0, 1, which corresponds to the subtraction operation. Therefore, the ALU output reflects the result of subtracting the selected B input from a selected A input. When the reset signal is set to 0, the output of the ALU is clear and becomes 0, 0, 0, 0. This output remains at 0 regardless of the input value until the reset signal is returned to 1 and another rising edge of the clock occurs, allowing the ALU to update its output again.